Welcome to Senior Lab for Chemical Engineering at UMass Amherst. Here we are in one of the lab rooms, and there are a number of different experiment stations. At each station, there's many different experiments that can be done.
Chemical engineering is a broad topic that can be applied to so many different fields, such as the industrial production of chemicals, the pharmaceutical industry, energy industry, and the environmental industry.
So we're going to take you on a tour of two of the experiments that we worked with that have helped us explore fluid flowing and pressure changes. That's going to be the fluid flow experiment behind me and the packed towers experiment. Why do we need to study fluid flow as chemical engineers? Any process we design or work with is almost certain to contain an element of fluid flow. A gas or a liquid, both of which we call fluids, will need to be transported from one place to another.
The big idea that links these two experiments is pressure change. Fluid flows from an area of high pressure to one of low pressure. Something has to change for the pressure of the fluid to make it higher so that it can flow to some place with lower pressure. For liquids, this is done with pumps. Pumps add pressure to the water.
And then, various obstructions that come along the way cause the pressure to change in different ways. Pressure is lost due to friction in pipes, fittings, bends, and valves that alter the flow of direction.
This is an Venturi flow meter, and though you can't see inside of it, inside it actually gets more narrow than this pipe. There's a throat that's only 5/8 of an inch thick, but within it there's also pressure meters. So it measures the difference in pressure between when the water is in the narrow part versus when it's in the wide part. Since water is considered incompressible no matter its pressure, it will take up the same amount of space. When a pipe narrows, the water will move at a faster speed, but will have a lower pressure. And as you can see in this animation, when the opening widens again, the pressure goes back up, but the velocity slows back down.
The fluid system is like a maze, the sort of puzzle for us to figure out. Before we turn on the pumps, we need to open and shut valves to make sure the flow is not blocked and goes through the pipes and fittings we expect it to.
So part of our experiment is to characterize this valve. To do this, we need to run the system at different flow rates to calibrate the flow meters.
Next, we'll run the system with the valve at different stages of opening and use our calibration data to determine the flow rate. Then we'll use the pressure change data along with equations for frictional loss to figure out the pressure change in this valve alone.
Finally, we take our data that comes from the computer that we collected and manually run some calculations on it and make some graphs.
Another experiment station where fluid flow and pressure drop is important is the packed towers. Here we have 4 packed towers, and one of the towers is see-through, so you can see what is going on.
Each column is partially packed with a certain shaped plastic packing material. These are designed so that when a liquid flows in from the top of the column, it will spread out over the packing and create a lot of surface area where it can come into contact with a gas being piped in from the bottom of the column.
When operated under certain conditions, a chemical like carbon dioxide that we want to remove from the gas will be absorbed by the liquid, allowing the gas to be released clean or used for another purpose, while the liquid can be used in some further chemical process.
To run this column, once again, we need to play with the valves, this time adjusting them very finely to get the system at a steady state when both liquid and gas are flowing through it in different directions.
We can determine steady state visually by watching the water level in the bottom of the columns. In the non-transparent columns, there's a visual gauge where we can monitor the water level.
Given liquid flow rate, how high we could let the gas flow upwards. There will be an ideal operating condition where a maximum amount of water and air would come in contact with each other, enabling this transfer of a chemical. But there is a limit. At some point, if the gas flow gets too high, the water will be held up in the packing material and bubble out of the top. This is called flooding the column.
Now in a transparent column like this, we can see when flooding starts to occur,
But how can we do that when we don't have any visual clues?
We can monitor the pressure change between the top and the bottom of the column. Since we have both fluids flowing and we increase the gas flow, the pressure drop between the top and bottom will increase, and as long as we have not reached flooding, it will remain relatively stable at its new value. However, if we have reached flooding conditions, the pressure drop value will not stabilize and it will start to quickly climb.
Once again, our group collected data, this time without the help of a computer, in order to determine ideal operating conditions for the columns at different liquid flow rates.
Fluid flow and pressure change are used in almost every system chemical engineers design or work with to improve the world. They are important in the production of medicines and vaccines, oil and gas, chemicals and fertilizer, alternative energy, and in systems that can help remove pollutants and greenhouse gases from our air and water.